This is about some work that was published quite a while ago at the Eurographics 2009, and as part of my master thesis. So it's computer graphics I really liked. So I would love to just briefly showcase this work, even though it's been a while, and that was done at the University of Siegen at the Institute for Vision and Graphics, as I mentioned, as part of my master's thesis. And it's based, it's about example-based rendering of eye movements, or learning-based rendering of eye movements. And so what we were dealing with here was the problems in facial animation with respect to eye animations, and we were looking at the problems that separating eyeballs from the overall face cause, and the problems with eyelids, having non-moving eyelids in eye animations, and so on and so forth. And what we wanted to do is to generate photorealistic renderings of eye movements as well as the surrounding tissue. And therefore what we did want is to model the eyes as a rotating 3D sphere. And we introduced a texture mapping approach for the displacement of the irises themselves, and wanted to learn the eye movement from input data sets in order to be able to transfer learned movements between faces. So the main idea starting with is to represent the captured eye movements in 3D scans in a 3D morphable model. And therefore what we get is a uniform 3D mesh representations, and we are able to morph new gaze directions. And that includes a deformation around the eyes and rotation of eyeballs. So here's an example. What we wanted to is to have what we have on the left is an original image, and then what we want to do is to replace the irises and also being able to move those. And so what we start with is the eyes in the 3D morphable model. And just as a quick summary, morphable models, 3D morphable models, introduced by Plants and Fetter, is in 1999, is to represent the face, represent faces by the same 3D mesh with a fixed set of vertices. And the idea is that we have a full correspondence between faces, so vertex I represents the same structure in all faces. And the idea further is to therefore solve the correspondence problem. That means that if we want to morph two faces, we do not want to have this blending effect that you see on the bottom left, but we want to have a morph between two faces, between the upper two faces, with perfect correspondence all the way. So we can basically morph from one face to the other. So, and that is based on shape and texture vectors. So what we have is a shape vector for the face face I, the shape vector Si, which basically is a vector consisting of the 3D positions, and for each vertex position we have a texture representation, RGB, a color, and that constitutes the texture vector for the face I. In this way, having this correspondence problem solved, we can actually form new shape vectors by summing over all or individual sets of faces. And this new shape vector is basically a linear combination of individual faces, each face influence being weighted by a weight vector, a weight value. And the same goes for texture vectors, and therefore we can generate effectively new faces. And now what we've been doing is to add gaze direction, and that's something we want to add to the model. And we first need to learn the information about eyelid movement by generating a model, a new data set, generating a new data set of here 9 gaze directions for a face that is brought in correspondence with the 3D morphing model. And basically we can do this. We did this in order to synthesize new gaze directions, and we did this in a course-defined approach. So we first established a course correspondence between the gazes and the morphing model, and then subsequently we refined this correspondence as the morphing model itself, coming from 3D scans only, did lack the degrees of freedom around the eyes. So it doesn't inherently, it basically means it inherently doesn't have these eye movements yet. So that's what we did to add eye movements, being able to synthesize new gaze directions to the model. And then in order to synthesize new gaze directions, once we established this correspondence with our dataset of 9 gaze directions, we were able to do a bilinear interpolation between 4 adjacent gaze directions, as you can see in this example on the bottom right, in order to interpolate intermediate gazes. So that's the first point, to refine the morphing model for the eyelid animation. And the second point is to have special treatments for the eyeballs themselves. Because as we were mentioning, we don't want to, in order to avoid these problems with separate eyeballs, we want to have the eyes and the eyeballs being represented in the continuous face mesh. And that actually, in particular, the occlusion of the iris, or appearing of the iris information, is of course difficult to handle in a continuous mesh. So there's different options that we basically explored, one being the interpolation of 3D vertex coordinates, which itself is inappropriate because we cannot add vertices to the morphing model or remove those, and what we get is just the triangle mesh being compressed or extended, which looks very unnatural. Another option is to simply interpolate textures, but that only generates these sorts of blending effect crossfades and not really a movement of the iris, so this is actually not what we want as well. As we've been mentioning already, the adding of a rotating sphere, separate eyeball, just generates artifacts and gaps, which is not very pleasing, so we don't go with this as well. Or different approach by basically having the sphere go through the mesh, we get these sharp transitions between the facial mesh and the eyeball, which is inconsistent with the sharpness of the face mesh itself, so it looks very unnatural. So finally we developed this option 4, which is an interpolation in texture space. So what we do is we have the eyes within the surface mesh. We have a separate texture map and an additional set of texture coordinates for each of the views, and then what we do is to morph the texture coordinates, and therefore the texture itself slides over the mesh within the eye regions. And again, we can do a bilinear interpolation of those texture coordinates in order to make the eyeball move virtually. And the interesting aspect is that we use the same coefficients for the shape deformation of the eyelids, and therefore the whole movement with eyelid and eyeball becomes consistent. So we faced several challenges while doing so. That was first the precise correspondence along the eyelids. and to get a smooth transition using alpha blending in the texture space, as I mentioned already, and to have one complete eyeball texture for each eye, and being able to manipulate the texture coordinates without causing distortions. So initially we looked at our 3D scans that were used for building the morphing model, and we're confronted with how to add the eye information now. So this is actually new. The 3D representation is based on the 3D texture information is based on having these positions X, Y, and Z, and we introduce these parameters U and V in order to surface parameters, and we rendered the eye information. As you can see here, the displacement of the texture from the original positions of the eyes into these upper corners in order to later extend those and being able to use those as our texture that is then blended into the model. So in order to get the correspondence of the eyelids, we first did a refinement of the morphing model, and we used an approach that was using as input basically 5 points per eye and per eyelid that were marked, that actually typically were 1 and 2 points in the corners of the eye, and then we had per eyelid 3 additional points, and then we fitted using a Catmull-Rom spline approach. We fitted a line into those points in order to define an eyelid in the space, and therefore we could generate masks. And so first of all, we could use this masks in order to estimate the original eyeball. So when scanning a model around the eyes having lots of reflections, the 3D scanners do produce arrows, and therefore, as you can see on the left, the original eyes tend to be not really spherical. So first of all, we use this approach of fitting these lines to estimate a sphere, to approximate the eyes using a sphere that were then fitted using these squares into with estimating first the center and then fitting an eyeball as approximated as a sphere. And then we replaced the old texture within the eye region, yeah, they were able to sort of generate a template on which the new eye texture later, without having any old artifacts of the old eyes. The new texture was then able to basically be morphed upon, blended upon, to generate these eye movements. And now there's the interesting part of warping the eyelids. So as I mentioned, doing the refinement on the correspondence on the eyelids and around them within this surface space. And what we did is, this is basically when moving the eyes later, what we want to have is the eyelids to move along with those. And this is basically the idea being that we, in order not to have the whole face move along with the movement of the eyes and only having the eyelids move, we define this sort of heat map based distribution approach, this sort of diffusion approach, where we say, okay, as you can see, this is here visualized with these intensities of the red values. The farther we move away from the eyelids, the less influence the movement of the eyes has on the surrounding mesh. So the interesting part with this warp is, given that it happens in this different space, it does leave the geometry unchanged. And this is, as you can see, this is the interesting part here. So as you can see on the right with these markings in this space, and we actually met the eyelids in this texture space, leaving the warp geometry unchanged. So now here is an example of synthesizing new gaze directions. As you can see, we have this bilinear interpolation on the top right that produces this new gaze direction. And as I mentioned, the eyes have been replaced by this skin color interpolation. And now in the next step, we're gonna do texture mapping to add the eyes to the model. And what we do is, again, in the texture space, we find in the representation of the textures of the 3D models, we find some place in the top corners to place the eyes. And this is where we use our texture coordinates later to actually map to map these eye textures into the appropriate positions. And we actually working with a few basic assumptions, which also constitutes a limitation to our texture-based iris movement model. That is that the iris is circular when it is projected orthographically on a frontal parallel plane. And the rotation of the eyeball is then approximated by a shift of the texture along this frontal parallel plane. So as I mentioned, we first define these position of the new eye textures within the overall texture. And what we then do is to define a vector in order to be able to access this texture. And yeah, there's a scaling factor that we add that does map the dimensions of the 3D space into the appropriate texture resolution. And here's a visualization of this accessing of the texture coordinates from 3D to our UV representation. And here again you can see this is this offset T, and then we have the scaling factor plus our position in the 3D mesh. It's for the X and Y coordinates. And here again we needed to do one more manual selection, that is of the pupil center. And yeah, what you can see here, this assumption that is basically being verified here, is that we have, what we did is to map a regular grid. And what you can see, even though when moving, maybe this is a little bit difficult to see here, but within the center on the top right picture, we have the center being mapped to the center of the pupil. These small little or tiny, I have to say, tiny red dots that you can see in the middle of the eyes, representing the center of the pupil, that is actually moving around or move to the left when looking to the left, and you can still see there's no distortions on the regular grid. So we have made a little verification of this texture mapping approach given these assumptions, so working with frontal or near frontal views. And here you see the counterexample, or why we're working with these new texture coordinates. So again, using the existing texture coordinates, which are basically bound to the shape coordinates, leads to these ugly distortions. And yeah, therefore this approach works because it requires to compute the texture coordinates depending on the vertex position. So finally, we did generate these eyeball textures, and the idea is that we can actually transfer eyes and eye textures using this approach, and here there could be different extensions. So for our example, our proof of concept, we basically manually completed the only partially visible eye information from the original scans. And as you can see, there's several approaches that we can go with. Here we work with manual completion, but you could also try to do scans with having the eyes wide open. So you basically, when moving, always have texture from one original scan that you can use without any holes or gaps in texture. Or maybe a very interesting approach would be that of doing an automatic combination of the original scans. Yeah, that however would require a person to have one could do have a person look into 9 different directions, for example, and then basically complete find a correspondence for the eyes and do an automatic completion. So this actually would be nowadays a very, very interesting approach, leading to very realistic eye textures that could be used further. And here's again this picture of doing a bilinear interpolation of gazes, but now as you can see, we add the eye movements together with the eyelid movement. So we have this mesh movement as well as the texture-based eye movement. Yeah, and then there's extreme cases, for example, closed eyes. So basically we use the same approach, and actually it works pretty nicely without distortions to a certain degree. Yeah, as you can see here, let's see this again. You can see here's the eyes closed, going from open to half closed to closed. Yeah. Now what we're about to do is to render the face model. Yeah, we're basically, while rendering, we can add some specular highlights in order to have the eyes look more glossy than the skin. And yeah, we were able to blend the face and the eyeball textures according to the alpha mask that we used before. That if you remember, this red mask that we can use to define the influence of the texture and the influence of the eye movement along the face. And this actually benefits this transfer to new faces. So what we can see here is on the left we have, based on the morphing model, we reconstruct this 3D model of the face from the picture on the left, and then we add the eye models, eye texture from this picture in the middle. And then we have these gaze directions, and as you can see here, we have these specular highlights around the eyes, these reflections here, these highlights. And yeah, so what we can do then is, so this is a video that's actually not working here, so I'm gonna put this up online as well. Now this is something shown in the beginning, this picture of having a replacement, and now as you can see there's a tissue movement as well. So let's see. We can actually do an animation of paintings as well. So here we do the same thing as with these with the pictures. We basically replace the eye movements, and I'm gonna put the video online as well. So to conclude, the main idea, I'm sorry, some restrictions here. What we didn't add yet were the eyelashes. as they were part of the overall texture. They're kind of like burned into the texture. So therefore, and also what we do have is shadows from the eyelashes, obviously, or otherwise on these eyeballs, which of course would be interesting. Then there are certain types of reflections with respect to the lens, and which are not as straightforward to implement, of course. And again, as I've mentioned, the eyeball is really approximated by a sphere, so it does not really represent yet an anatomically correct model. Benefits, however, is that we get a solution for photorealistic eye movements in a morphing-based facial animation setting, and therefore we avoid a number of discontinuity artifacts, and also achieve a new paradigm, which is to use textures on 3D meshes using these texture coordinate approach. The manual interaction, as you have seen in our approach, is reduced to only clicking a few initial points, so this is actually pretty nice as well. Yeah, so this is it, and yeah, finally here's a small version of this painting animation. No, you can see it, but again, we basically do the same thing as with these with a picture below with the two pictures. So actually, what you see here is we were painting. We extracted the face as represented as a 3D model, did the gaze animation here without interchanging the eye textures. Just basically, we've completed the eye textures and then basically had it move upwards with the eyelids being pulled up. And then we rendered this back into the image itself, and this is the picture on the top right that you see. On the top left is the original, and actually doing this and having this movement and writing out frame by frame, we can actually generate this video that are going to be put up line that you see online as well, and basically see this person on the painting looking around. So it's pretty fun. Okay, so yeah, thank you, and that's about it.